So we can also look at a particular case, zeroeth order reaction. So in a zeroth order reaction, we don't have zero molecules. Instead, we have a situation where the reaction rate isn't dependent on the concentration of A anymore, okay? So we'll draw a case. In this example, we're going to look at the formation of a catalytic complex, and then that dissociates. So if we'll have a bunch of A floating around, and then we'll have some small molecule Z. And when A and Z come together, we have some A, and then we have our complex here. A, Z. Okay. And interaction with that Z molecule is what converts A into the product C. So now we have A. We don't lose our Z, it's still there. And now one of the A's has been converted to C following that interaction. In this case, the change in concentration of A with time is equal just to negative K. The formation of C with time is equal to positive K. The rate is considered independent if the concentration of Z is very small. This is sort of our rate limiting factor, and it's what's controlling the rate. But for our cases, we're going to think of everything in terms of concentration of reactant A. And since we know it's sufficiently high enough compared to whatever this catalytic molecule is that's coming in, we'll go ahead and we know that A is not actually changing with respect to A's concentration. And so then once again, I'll just rewrite this so you have it. By convention, we're going to let our rate constant K always be positive. And we have sort of for a general nth order case. So it could be something like A plus B plus C plus D is going to E or whatever it might be. For this general case, K is going to have units of m to the 1 minus n s to the negative 1. So 1/2 is always going to be in the bottom, and what else has to be in the bottom is basically 1 less than the number of n's that we're at. So up here we were at second order, n is 2, so we have 1 minus 2 is to the negative 1, m's in the bottom, same thing here, n would be 3, 1 minus 3 would be m to the negative 2, that's molar squared in the bottom. It's just our generic keeping track of our units. Okay, so in order to calculate the actual concentration dependence with time, we're going to integrate our rate laws. So we can start with the 0 case. We'll do 0, 1, and 2. And then I will point you to the page of the book that has the general case, so how to do more sophisticated ones. So for our 0th case, we have concentration of A changing with time, which is equal to negative K, our rate constant. So just rearrange this. I'm going to integrate on this side from some initial concentration, A naught. Put it out here so it's obvious. Up to some final concentration. And on this side, we're going to integrate from 0 time to some time t. Here we're just going to have our final concentration minus our initial concentration equal to our rate constant times time. How do we get K? Like in real life, how would I get that? Any guesses? Perfect. So what Jenny said is measure the concentration of A as a function of time. You get K by running that rate constant by running it experimentally. So we've already talked about, or alluded to some ways. You're going to put in some initial concentration that you know of, that you control. And over time, you could take some measurements, or you could wait an amount of time and take a final concentration. And again, we said there's a lot of ways to measure this. Maybe we're looking at radioactive decay. Maybe we're looking at fluorescent changer, or usually something related to light or optical measurements is a popular way to do this. Okay, so we'll look at that change in some optical output so that we know that our concentration has decreased, and then we can calculate a rate constant for ourselves. So if we plot for our zero order reaction, we'll do time in seconds on the x-axis, and let's put reactant in molar on the y. In this case, we're talking specifically about A. This could be, this be 1 molar, just 1.2. 1, 2, 3 cycles. So you could have all sorts of curves that look something like this. This direction, we have lower values of our rate constant. So we move in this direction, we have higher values of our rate constant. We look, say right here, maybe for this case, our change in concentration went from, we started with 1 molar for our initial concentration, we went down to 0. So 0 minus 1 molar would be equal to negative K times, I don't know what that is. In my notes I made it 3.5 seconds. It looks nothing like that, but pretend it does. Negative 1 over negative 3.5 seconds, we could get a K value of 0.28 seconds to the negative 1. So you could run this experiment, plot your data, and calculate a rate constant that way. If you see a plot of this stuff, be able to calculate it. So make sure you know how to read and interpret these plots. So for the zero order reactions, the concentration of products now, talking about products, is going to increase linearly with time. For A versus T will be a linear plot. That's what you should expect to find. Or if you do plot these two things and you see a linear plot, then you know you're talking about the zero order case.